Okay, so let's look at a problem that it looks pretty difficult, but as we go through piece by piece, I think you'll sort of see it's the same old, same old. Okay, so in this package, or packet, the new packet on page 3, I just got this problem right off of here, okay? I put that on top of it. You don't have to cut that out. I just wrote it like this, okay? So we're going to put that in our notes, and we're going to find the equation of the tangent line at -1, 2, okay? So we're looking for a line that goes right here, okay? Now, this is in implicit form. This is an ellipse right here. And so, like I said, we didn't have a lot of chance to work with these last year, but just kind of note that it sort of looks like a circle. A circle has an x squared and a y squared, but notice it has a middle term. Okay, so for right now, you don't ever have to come up with the graph or anything like this. Okay, so if we're finding the equation of the tangent line, remember that what we need is a point and a slope. Well, we have the point, so all we need is the slope. Okay, so that is my goal. I'm going to find the general form for the slope, and then I'm going to plug in that point, and then I'll be able to write that. Okay, so I'm going to do d dx of x squared minus xy. xy, I see the product rule right there. Okay, plus y squared is d dx of 7. Okay, so now let's go through. Derivative of x squared is 2x. And you'll start to notice like the same one keeps coming up. So let's look now. I got to be careful about this minus right here when you're doing a product rule, because you're going to have to use a parenthesis because you have to distribute that. So just watch out for that. Okay, I'm going to do the first derivative of the second plus derivative of the first, which is 1, times the second. Okay. Derivative of this is 2y dy dx. Well, I didn't leave myself much room here, did I? Equals 0. Okay, so let's just clean that guy up. Let's see, we've got x, negative x dy dx plus 2y dy dx. Okay, so this is a 2x. This is going to become a negative y, so it's going to come to the right. It's going to be a positive y. Okay, so then I'm going to write that dy dx. And I'm skipping a step here, so I'm going to write, but I factored it out. I think you guys should be okay with that. Instead of writing negative x plus 2y, I'm going to write 2y minus x. Just, it looks better if your leading coefficient is not negative, if you can do that. Okay, so remember, all I did is I factored out dy dx, and then I divided both sides by that. Okay, so this right here, remember, this is the general formula. This would give me the slope at any point on this ellipse. I could put in any point that I wanted, and that would give me the slope. But I specifically want it at the point -1, 2. Okay, so I'm just going to go, okay, that's 2 minus 2, -1, over 2 times y minus -1. And it looks like we're going to get 4/5. Okay, we have our point, we have our slope. So y is 4/5, x minus -1 plus 2. And I actually just worked it out all the way, just because it said that we needed to graph it. And so I want to put it in the form that I can graph with. Okay, and then it also will allow me to check if I did it right. Like if this line looks nothing like a tangent at that point, then I've made some mistake. Okay, so I know I'm at the point -1, 2. So I'm at this point right here. Okay, the tangent line says it should cross at 2 4/5. That looks about right here, right? Right up there. And that the slope is 4/5. So I could go down 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, kind of over there somewhere. Okay, so that is looking, okay, I don't know like how accurate this is going to look, because I don't have a big enough piece of graph paper. But I can see, yeah, I'm right. It's going in the right direction. It looks like what it should look like there. Okay, so part B, we're going to find the equation of the normal line. At -1, 2, and we're going to graph that as well. Okay, well, piece of cake, right? We already know that the equation of the normal line, that all we have to do is find the reciprocal. The slope of the tangent line was 5/4, so we know that the new slope, or excuse me, the tangent line was 4/5, so the new slope is going to be -5/4. So y equals -5/4, x plus 1 plus 2. And again, I worked that out just so I can check it because it wants me to graph it. So -5/4 x plus 3/4. Okay, so let's see what that's going to look like. I'll do this in a different color. Okay, so if its y-intercept is 3/4, so it's about right there. Its slope, I'm going to go down 5/4, so 1, 2, 3, 4, 5, 1, 2. Okay, so kind of going off the paper, but it's looking pretty darn good right there. So I'm pretty positive we did it right. Remember that the tangent line and the normal line are always perpendicular to each other. Okay, so not as bad as that one looks. So sometimes I think these little graphs can be kind of scary looking. Okay, other thing we're going to look at is calculating higher order derivatives. Like I said, I think these are really fun. I don't know why I love implicit differentiation, but I do. Okay, so let's say we want the second derivative of one of these. And again, I just want you to think about it as a little puzzle. So let's do calculating higher order derivatives. So that we're finding, we're going to call it d squared y dx squared. Okay, remember that's one of our notations. Okay, there's some rules that you want to go, or you want to do. Okay, first thing you're going to do is you're going to solve for dy dx first. Okay, got to do that. Okay, now what always ends up happening is that the second derivative will always have a dy dx in it. And so what you're going to do is you're going to substitute it with the solution that you got up here to dy dx. Okay, so that solution that you got in step 1. Okay, then the third thing you're going to do is you're going to look to see if you can make more substitutions. So it's going to be kind of like a little puzzle. Okay, so let's look at an example. Let's find d squared y dx squared, or the second derivative of cosine y equals x. Okay, so first thing I've got to do is I got to find dy dx. Okay, so let's do that. Okay, so I can tell here that I've got a chain rule problem because the mommy function would be cosine x, but mommy's now carrying a y. Her little baby's a y. Okay, so we're going to say derivative of cosine is negative sine, leave the baby in, and then take the derivative of the baby, dy dx. The derivative of x is just 1. So we know that dy dx is negative 1 over the sine of y. Now, I'm thinking I'm going to be using this later on, because remember, when we find the second derivative, we're going to find that there's a dy dx in it, and we're going to replace it with that 1 minus sine y. Okay, so now I'm going to take the second derivative, so that d squared y dx squared, and actually I could do this, of negative 1 over the sine of y is equal to, now I'm gonna rewrite this guy. Let's rewrite this as negative sine of y to the negative 1, because I don't want to use the quotient rule. Okay, so we've got a chain rule here. We've got 3 of them, because we've got this function right here, x, like think about this as 1 over x. Okay, so we have that function, then inside that function we have the sine function, and inside the sine function we have the y. Okay, so I'm going to take the derivative of this. I'm going to bring down the negative 1, and that's going to make it positive. So I'm going to leave the baby in, and it's going to go to negative 2. Okay, now I'm doing my chain. So I'm on the inside. Well, the derivative of sine is cosine. And I got to leave the baby in, which is y. Okay, and then I got to take the derivative of y, which is dy dx. So see how that dy dx came up again? And we know that dy dx is negative 1 over the sine of y. So then this becomes the sine of y to the negative 2 cosine y times negative 1 over the sine of y. Okay, so all I did was I substituted right here. I substituted in that. Okay, all right, and then we end up with that d squared y over dx squared is going to be, it looks like negative cosine y. What do we have left up there? Over, here's a sine squared y on the bottom and another sine of y, of sine cubed y. And that's it. Alrighty.